derive all. I will derive just what will be the moment of inertia for the rod and what will be the moment of inertia for the ring. The other one, I will give you the formula. Every time you have those objects rotating, you need to use those moments of inertia. Those are constant, which I usually give in the test. So, for example, how can I find the moment of inertia of a rod that is rotating with respect to the center of mass? Let's say the rod is rotating with respect to the center of mass, like this, from the center. What will be the moment of inertia of this rod when it's rotating with respect to the center? In order to apply this, so we will say we want to find the moment of inertia with respect to the center of mass. So in order to find that, we will take a piece of this element and we will call dm. And the length of this dm is dx. The variable of integration is x, which is the distance from here to here. If we want to find the moment of inertia, we need to integrate from here to here, but we multiply by 2 because we also have this moment of inertia. So the integral I for the rod with respect to the center of mass will be twice this and this. The integral from 0 to L over 2, from 0 to L over 2, of r squared, which in this case is x, the distance from here to where we have the mass, dm. But I of the rod with respect to the center of mass will be 2, the integral from 0 to L over 2. Now we need to change this with the spatial coordinates. So if we know lambda, or if we have lambda, we can replace dm by a spatial coordinate, lambda dx. So instead of writing this, I will write lambda dx. If lambda is constant, I can move this lambda out of here. So will be 2, I move the lambda out, and the integral of x squared dx, how much is that integral? From 0 to L over 2. What is the integral of x squared dx? X cubed over 3. So will be 2, and what is lambda? If it's uniform, m over L. So if I have the mass of this, and I have the length of the rod, I can replace by m over L times this integral, which will be x cubed over 3. From where to where? From 0 to L over 2. So I come here, and I said that I of the rod, with respect to the center of mass, will be, now I substitute, I get 2m over L cubed over 8 times 3 is 24. 24 and 2, we get that this square, and we get 2 and 24, 12. So we get ml squared over 12. And that's the moment of inertia of the rod. So this is how to derive, or how to find the moment of inertia of the rod with respect to the center of mass. Any question? You can also integrate from negative L over 2 to L over 2, and you don't have to multiply by 2. So you can integrate here from negative L over 2 to L over 2, and you don't have to multiply by 2. Will be the same thing. Or from 2 and 0 to L over 2. Yeah.
What happens to 3?
To the 3.
X cubed over 3.
Okay, so we have the 3 here, and when you have L over 2 cubed, this will be L cubed, right?
Right.
And 8 times 3, how much?
Okay, that's 24.
24. Then you calculate. Alright, that's the moment of inertia of the rod with respect to the center of mass. But sometimes the rod is rotating not with respect to the center of mass, but it's rotating with respect to the end, like this. So sometimes it's rotating like this, but sometimes, like the grandfather clock, the object rotates like this, correct? The rod. So in the engine, so you will see, well, okay, when we will use all this, all right, let's say, you know that the engine has, how you say, crankshaft or something like that, right?
Yeah.
So this is like a rod rotating inside the engine, right? You have the grandfather clock. So you have those objects that or those crane or whatever that take oil from, the oil, and you can see it constantly, like moving like this. So all these are things where you have rod rotating. And this is why we learn how to get the moment of inertia, how to get apply the rotation to this type of objects. Okay, this is the rod, but what will happen if it's with respect to the end? Applying the same thing will be, if this is with respect to the end, how can I get the moment of inertia? So now I want to find the moment of inertia of the rod, not with respect to the center of mass, but with respect to the end. That will change the moment of inertia. So you will do the same. You will find dm here, and this is dx. And now we will start integrating from here to here, which is my x. You go back to this equation. I is the integral of x squared dm. We substitute from where to where? You will integrate now. From where to where? The limit of integration.
0 to L?
From 0 to L. So now my integration will be from 0 to L. So I am integrating. Remember that the integration is the summation of partition, right? I will integrate up to here, from 0 to L, x squared, but now dm I will replace by the spatial coordinate, which I come to here because it's linear. I will replace by lambda dx. Lambda constant, I can pull out. So will be lambda, the integral of x squared dx. What is the integral of x squared dx? Again?